Okay, so this is the last of the lecture that we had on chillers, and we left off back before break talking about cooling towers. So just to review real quick, there's two typical configurations for cooling towers. We can either have a counterflow type of cooling tower where the air is rising up vertically through the cooling tower, or counter to what the current stream of water is heading in. So like this one over on the right would be an example of a counterflow cooling tower, because the air is coming in on the sides and then going up in the opposite direction of the water flow that's going to be dropping down through the cooling tower. Crossflow types of cooling towers are ones like the one on the left, where we're going to have the water falling down through the cooling tower, but then the air is going to be going across and perpendicular to the flow of the water through the cooling tower. This is an example of a larger size cooling tower. These are ones you'll see on large commercial buildings. If you go down to Dartmouth Hitchcock Hospital in Lebanon, New Hampshire, you'll see at their chiller plant, they've got a big series of these all stacked together. But these large ones, as you can see, there's a ladder going up the side of this unit, so it's large enough to where you could to climb up on a ladder. You'd be able to come up here to the top of the unit and walk around on it, so there's a perimeter handrail on it. But these units are filled with, as they note here, a PVC fill, and this is basically a material that the water runs down over, and it helps create additional surface area. And as they note here too, it also helps eliminate what they call drift, which is where the water could get blown off of the cooling tower by any wind. So it helps keep the water contained inside the cooling tower, and we don't have any loss or as much loss from the system. There's a video that I've got as part of this bit on cooling towers. It's a little demonstration on how cooling towers work and the whole operating idea of them. So I'll post this link onto Moodle, and you can watch that after you watch the lecture video. It gives a pretty good description of how the whole system works, and talks about makeup water for the unit, and how we need to add different things to the system, but also how evaporation leaves behind lots of minerals, and we have to keep adding water to the cooling tower to maintain the concentration of minerals and build up below a certain level, and basically dilute that concentration with fresh water. So the big thing with cooling towers, the whole point of them is that they're supposed to be able to cool down your condenser water that's coming from your chiller. So remember that the chiller inside of our building is going to be creating chilled water for the building, and the evaporator barrel, we're chilling that chilled water loop for our building, and then that heat's getting rejected to the refrigerant. It's going through the compressor, and then it's going over to the condenser barrel. So in the condenser barrel, there's going to be a separate condenser water loop that's going to have water going through it, and that's going to be the water that we're going to reject the heat from that hot refrigerant on the condenser side over to the water, and then condense the refrigerant back down into liquid form. So when we talk about cooling towers, all of the performance values on a cooling tower, a lot of it's dependent on what your local wet bulb temperature is, and then what is the leaving water temperature, the entering water temperature, and then also the flow rate through the cooling tower. So in the ASHRAE book, this is where we would go to the weather data tables in the book, and then we would look at the evaporative cooling conditions, and that's where they would give us the design wet bulb conditions, and we can get the 1% or 2% design wet bulb temperatures, because that's going to be a big driving factor. One thing to note on cooling towers is that the tonnage on a cooling tower is slightly different. So, traditionally we've talked about chillers and all of our other refrigeration units, that 1 ton of cooling is equivalent to 12,000 BTUs per hour of heat absorption. But on a cooling tower, the way that we rate a cooling tower is every 1 ton of capacity on a cooling tower is equivalent to 15,000 BTUs per hour of heat dissipation. So at the cooling tower, for every 1 ton of capacity that we have, we're going to have 15,000 BTUs, or approximately 15,000 BTUs per hour of heat dissipation. This would still match up ton for ton with your cooling side. So the 1 ton and 12,000 BTUs on the chilled water side, and 1 ton and 15,000 BTUs per hour on the condenser water side. Because the other piece that we have to deal with on the condenser water is we have to remove the heat that's gained from the compressor. So the refrigerant's gaining energy from the water on the chilled water side, on the evaporator side, but then again, the compressor's doing additional work on the refrigerant, and so we have to reject that additional heat from the system as well. So the way we get the 15,000 is if we take 3 gallons per minute per ton for the cooling tower. If we assume that that's our standard flow rate of 3 GPM, and if, say, for example, I assume entering and leaving temperatures of 95 degrees Fahrenheit, so it's going to be the water coming from the condenser on the chiller, and then it's going to leave the cooling tower at 85 degrees, and I've got an ambient wet bulb temperature of 78 degrees Fahrenheit. If I do the calculations, if I take my 500 times GPM and then times my delta T, which is going to be the difference between my 95 and 85, that's how I get my 15,000 BTUs per hour. When you talk about cooling towers, there's 2 terms that you'll hear engineers use a lot, and they talk about what's the range of the cooling tower, and they talk about what's the approach. The range is the actual temperature difference that you can achieve on the cooling tower between the entering and leaving water temperatures. So like on that previous example, the 95-85 differential is a 10-degree differential, and so we would say that the cooling tower has a range of 10 degrees. So it's saying how good of a job can the cooling tower do of cooling that hot water that's coming in, and what temperature will it cool it down to when it leaves. With that 10-degree range, if I was at some other temperature like 94, then I would assume that the leaving water temperature is going to be 84, and I'm going to maintain that 10-degree range. The approach is the measure of how close are we getting our leaving water temperature to the wet bulb temperature of the air outside. So how close are we approaching that wet bulb temperature? Our max theoretical limit for what we can cool that water down to is going to be our wet bulb temperature outside, but we're not going to ever really be able to truly achieve that value. Our cooling tower, it'd be great if we could get to 100% efficiency, but the reality is we'll never get there. But we can get close, or we can get down to a certain point, and that's what that measure of approach is. So the smaller your approach, the smaller that value is, the greater efficiency you're getting on that system because you're approaching that wet bulb temperature outdoors. We can use these terms to define the efficiency of a cooling tower as well. So the efficiency of a cooling tower, we call it eta sub W, is going to be equal to the range divided by the approach plus the range. So I can go through and I can calculate my range, and I can calculate the approach, and then I can plug it into this equation. Or if I take these variables in my equations up here and I sub them in to the equation, my down in the denominator where I'm doing the range or the approach plus the range, the wet bulb temperature, or the water temperatures leaving the cooling tower, that TW out, cancels out, and so my equation becomes the temperature of the water coming into the cooling tower, so T sub W in, so the W here stands for water, and it's the incoming water temperature, and then minus TW out, which is going to be the leaving water temperature, and then divided by the temperature of the water coming into the cooling tower minus the temperature of the wet bulb temperature of the air that's outside, and that's going to be moving through the cooling tower, and that's going to be picking up the heat from that water. So for cooling tower efficiencies, one rule of thumb that always occurs with cooling towers is the higher our wet bulb temperature is outside, the lower our efficiency is going to be. So like in the southeast US, where we've got hot, humid summers, if it's a really hot, humid day, our cooling towers outside are going to end up with some lower efficiencies because they're going to be operating in these very moist conditions, and there's not a lot of ability to reject heat and moisture to the outdoor air that's already so hot and humid. In places like the West and the Southwest, where the climate is more dry and arid, you can get some better efficiencies on the cooling towers because the wet bulb temperatures are so low. So if your wet bulb temperature increases, it's also going to not be the only value that changes. Our cooling towers are designed for a certain approach. So when the wet bulb temperature goes up, your leaving water temperature is going to go up too, because again, we can get to a certain point within range of our wet bulb temperature, but we're not going to usually be able to get any closer. So if I'm at 75 and now my wet bulb temperature goes up to 78, my leaving water temperature, I'm going to expect to see that go up by 3 degrees as well. So typically in a mechanical draft cooling tower, you're going to see your water temperature have an approach of about 5 to 6 degrees is a typical approach value. So usually within 5 to 6 degrees of your ambient wet bulb temperature. So for an example, we want to calculate for the values of 95 and 85 that are my entering and leaving water temperatures and a wet bulb temperature of 78. I want to figure out what is the approach, what's the range, and what is the efficiency of the cooling tower. So if I calculate the approach, it's going to be, again, my temperature of my water going out minus my wet bulb temperature. And so for my cooling tower, in this case, I've got 85 degree water leaving the cooling tower, and the wet bulb temperature outside is 78. And so that's going to give me an approach of 7 degrees. For my range, again, it's going to be my water temperature coming in minus my water temperature going out. So in this case, we've got 95 minus 85. And so that's going to give me a range of 10 degrees Fahrenheit. If I go to calculate the efficiency, remember that it's going to be my range divided by my approach plus my range. So I'm going to get my 10 degrees of range divided by, it's going to be 10 plus 7, which is the same as 10 over 17, which then if I calculate it, I should get that it's 58.8%. So if you calculate that, it'll come out as 0.588, and then just putting it into a percentage, you would calculate that it's 58.8%. Okay, so that's it for this lecture. Again, I'll post the video link that I referenced before. It's a YouTube video link for those descriptions of cooling towers. I'll post that to Moodle along with this video. So hope everyone has a good weekend, and I'll see you on Monday.